All right, folks, here we go with our example. Consider the lamina bound by the curves y equals x, y equals sine x, and x equals pi, which I've illustrated below here and shaded in yellow. Part A, find the center of mass of the lamina if the density at any point in the lamina is proportional to, geez, I wasn't even paying attention when I was doing this. It is proportional to the distance from the y-axis. So, what does that mean? Well, we should start with our density function. So for A, density is going to be a function of x, and if we draw a strip in here, let's see. Let's get a blue approximating strip in here. Approximating. No, stop it. Oh, come on, man. Small children in other countries know what I'm trying to draw. Get some AI here. Okay. Anyway, there's my approximating strip. Now, its distance from the y-axis, generically speaking, is x. And so the density is proportional to the distance from the y-axis. So we just get a kx there, where k is a constant of proportionality. And we're going to assume k is greater than 0. Come on, we're going to assume that I can't spell either. Proportionality. K greater than 0. Which basically means this plate gets denser as we get further and further to right. So typically in an engineering setting, if you wanted to illustrate that, you might make this sort of darker and darker and darker as you go to illustrate that it's getting denser and denser and denser and denser and denser. I don't know if you can really tell. That's what I was trying to do there with the shading. Doesn't matter. Anyway, let's get after it. Anytime you want to find the centroid and there's no symmetry involved, as we see here, there's nothing symmetric about this region, you're going to have to do 3 integrals. Why 3 integrals? Well, you got to find x bar and you got to find y bar, but both of those depend upon the mass. So let's go over our formulas. X bar is equal to the integral from a to b of the density function times x times the upper curve minus the lower curve dx divided by the integral from a to b of the density times the upper curve minus the lower curve. Now, typically, and what we want to note here is, since this is the mass, typically we write this a different way. So if this is mass, we actually write this as 1 over m times the integral a to b of rho of x times f of x minus g of x dx. So where m, not n, where m is the mass, and y bar can actually be written the same way. It's 1 over the mass times the integral from a to b of 1/2 the density function times f squared of x minus g squared of x dx. So let's get started. Integral number 1. The mass is equal to the integral from a to b of the density times the upper curve minus the lower curve dx, which in this particular case is the integral from 0 to pi of the density kx times the upper curve x minus the lower curve sine of x dx. So the k here is constant. We can factor that out of the integral. This is k times the integral from 0 to pi, and if we FOIL this out or multiply it out, we get x squared minus x sine x dx. Okay, So let's integrate this. This is k. The antiderivative here is 1/3 x cubed minus, let's see, this is going to be a tabular form integration by parts. Let's crank this out really quick. Here we have x. Sine x will differentiate one column, we'll integrate the other. This will be 1, 0. This will be negative cosine, negative sine, plus, minus, plus, diagonal, diagonal. And this becomes, let's see, minus x cosine x plus sine x, all evaluated between 0 and pi, and this will become k times 1/3 pi cubed plus pi times negative 1 plus 0, and when we plug in 0, we get 0 for all of our terms. And so this becomes, let's see, let's get a common denominator here. This is k times the quantity pi, let me write that better. K times the quantity pi cubed minus 3 pi all over 3, and that is our mass. And if you want a helpful hint, I would suggest that you rewrite your mass as a single fraction, as we're going to be taking its reciprocal in the next formula. So let's get started with x bar here. Our second integral for x bar is 1 over the mass times the integral from 0 to pi of the density function times the distance times the area of a slice, which is f of x minus g of x dx. Plugging in the information that we have, the reciprocal of the mass is 3 over k times pi cubed minus 3 pi. The integral from 0 to pi of the density function kx times x times the upper curve x minus the lower curve sine of x dx. Cleaning this up a little bit, we're going to see a couple of nice things. You're going to note here that since k is constant, it's going to cancel out of the problem, and our center of mass no longer depends upon the constant of proportionality. So that's nice. Let's see, what else are we going to get here? We're going to get 3 over pi cubed minus 3 pi times the integral from 0 to pi of x cubed minus x squared sine x dx. So this is going to be 3 over pi cubed minus 3 pi times the antiderivative is 1/4 x to the 4th. And let's go ahead and do a quick tabular form here. I'll use negative x squared. And sine x will differentiate one column, we'll integrate one column. Aren't you glad you learned that tabular form so that you can go like this? Negative 2x, negative 2, 0, negative cosine, negative sine, cosine, plus, minus, let's just do this. No, that's fine. Plus, minus, diagonal, diagonal, diagonal. And this is going to be a plus an x squared cosine x minus 2x sine x minus 2 cosine x, all evaluated between 0 and pi. So this will be 3 over pi cubed minus 3 pi times the quantity pi to the 4th over 4 plus pi squared times negative 1. The sign of pi is 0, so that term will be 0, and then minus 2 times negative 1. And when we plug in 0, the first 3 terms are all 0 because of that factor of x, and then we'll get a minus 2 times 1. And this will become 3 over pi cubed minus 3 pi times pi to the 4th over 4 minus pi squared plus 4. And I don't know that that's going to clean up too fantastic, but it probably turns out to be a perfect square or something ridiculous, right? Let's see. 3 over pi cubed minus 3 pi. And then if I get a common denominator of 4, this will be pi to the 4th minus 4 pi squared plus 16. No, I don't think that that's a perfect square at all. Doesn't matter. We can get a decimal approximation for that. This is, after all, an engineering problem. So let's do that. And this becomes, let's see, about 0.139 times about 18.483. If we multiply those together, I'm carrying a lot of accuracy here on my calculator, times 0.139, you get about 2.570 roughly. And that is x bar. All right, let's find y bar. So for our third integral, y bar is 1 over the mass times the integral from a to b of 1/2 the density function times f squared of x minus g squared of x dx. And in this case, we have 3 over k times pi cubed minus 3 pi, the reciprocal of the mass, from 0 to pi, 1/2 the density function, kx, times the upper curve squared minus the lower curve squared, dx. Now the integrals are getting a little interesting. Again, what we notice here is the k values are going to cancel. And if I factor out all the constants here, we now have 3 over 2 times pi cubed minus 3 pi. The integral from 0 to pi of x cubed minus x sine squared x dx. And hopefully you're getting well versed in the art of integrating things like sine squared. This is 3 over 2 times the quantity pi cubed minus 3 pi. And I'm going to pause here for just a second as you guess what I'm about to do. Ready? Dramatic pause. You guessed it. I'm going to use a reduction of power formula. This is 1 minus cosine 2x dx. So this is what we have. 3 over 2 times the quantity pi cubed minus 3 pi, integral from 0 to pi of x cubed minus 1/2 x plus 1/2 x cosine 2x dx. And we'll use just a little bit of integration by parts on that last integral. So this is 3 over 2 pi cubed minus 3 pi. The antiderivative here is 1/4 x to the 4th minus 1/4 x squared plus 1/2 the antiderivative of x cosine 2x, which we can also use integration by parts tabular form on. We'll differentiate and integrate. This will be 1, this will be 0. This will be 1/2 sine 2x, and this will be negative 1/4 cosine 2x plus minus plus. And again, if you have no idea what I'm doing right now, you should really go back to that integration by parts video about tabular form and review it now. That's all the way back in section 7.1. I think that this is a level 2 integration by parts problem. And what we get here is 1/2 x sine 2x plus 1/4 cosine 2x. And I'm going to move this out of the way here. There, that's better. And this is evaluated between 0 and pi. Cleaning this up, we have 3 over 2 pi cubed minus 3 pi. Plugging in pi, we again get pi to the 4th over 4. Now we get minus pi squared over 4. At least they have a common denominator. Let's see here. Plus 1/4. The sine of 2 pi is 0. And then plus 1/8. the cosine of 2 pi is 1. And then when we plug in 0, we get 0, 0, 0. 0 minus 0 plus 0 plus 1/4. And this becomes 3 over the quantity 2 times pi cubed minus 3 pi times pi to the 4th minus pi squared over 4. And let's see. Let's see. An eighth minus a fourth is minus 2/4. So let's just get a common denominator there. Yeah. Minus 2. And we'll get a decimal approximation for that guy. Let's see. Previously, this particular piece was 0.139. So this is 1/2, 0.139 roughly. And let's see. Pi to the 4th is about 97.4 minus the quantity pi squared. It's going to be about 87.5 minus 2. It's about 85.539, all divided by 4. And that's approximately 21.385 to 3 decimal places. So we'll cut that in half. And then we'll multiply times 0.139. And we get approximately 1.486. So, in the grand scheme of things, we have y bar and x bar. So let's go back up to our illustration. Apparently, let's do this in red so we know that it's after the fact. X bar was about, what was that? 2.57. 0. Y bar was about 1.486. So, looking at our diagram here, let's see. Pi is about 3.14. Pi over 2 is about 1.5. So 2.5. Yeah, well, that's pretty close actually. And then 1.4 is going to be right about here. It looks like I'll draw it big, so there's some error there. X bar, Y bar. That seems to be the center of mass for this object. Okie doke. Well, there you go.